welcome to another Draft Physics video presentation. DraftScience here on YouTube. Something like that. So Professor Lewin, don't get old. It's not good for you. Frankly, he was always silly. He's just gotten sillier. But anyway, this is the whole problem with physics is trivial, and uncareful. It's probably a better word, for kind of this simplistic, again, trivial inspection. Trivial is examination. It's just a trivial view of the crime scene and falling for the murderer's little tricks kind of thing, like just the obvious evidence. And not going deep enough to figure out that it isn't right and it needs to be fixed. And they just ignore all of those problems, like wave particle duality. It doesn't make any sense. The fact that you don't have energy for your gravity equations, essentially you're making this up. We'll borrow it because we give it back later kind of notions. That can't be right. So, it's just unfortunate that, being smart is more complicated than it used to be. In the old days, being smart was, you could count to 10, and being smart had more to do, more connected with reliable tests. Your intelligence was always tested. And there is no tests for these more... in this more complex world. And so they do things like allow people to stand up and have a press conference and go, we did it, and have such a convoluted what they did that nobody bothers trying to figure out whether they actually did it or not, because it's not possible. It'd take you a year with 100 computers and people working 8 hours a day to figure out they didn't do it. So there's no way to test it. There's no way to know whether they did anything or not. Unless they videotaped what they were doing, and then we could all just watch the videotape and see how they're cheating the hell out of the reality. How the device is a convoluted pile of shit. It's just a Rube Goldberg that intends to prove that, see, if a boot hits a rock over here, ducks quack. And it's just, they've engineered it so that's what it does. But there's no real connection between the boot and the duck quacking. The duck's just quacking because you made a device that quacks. Come on. But anyway, I really don't know how to say all this stuff I want to say about my observation that's the critical error here is that, yes, everything's gotten too complex for an individual or a small amount of intelligence to scrutinize what intelligence is calling intelligence. And I guess you could even go into this whole argument of there's a lot of smart people who are playing with words like agnostic instead of saying atheist, when it doesn't make much sense, because the simple truth is you're saying I don't believe in fables. So until you show me evidence, I don't believe in made-up characters. All of them. Doesn't matter which ones. The cartoons, the fables, religions, it's all the same thing. These are just stories. I don't believe stories just speedy. Somebody says they caught an elephant fish. No, I don't. Prove it. I don't have to believe in elephant fish or the possibility of elephant fish or any of that kind of crap. The mere fact that it's possible elephant fish exist, I could imagine one, doesn't mean I have any obligation to say I'm agnostic on the subject of elephant fish. Well, anyway, it's just this whole breakdown of logic and intelligence, in the sense that everybody has specific intelligence now, and it doesn't have any... it doesn't cover the basic rules of getting right answers, which is be really careful. That's one of the first rules. Be very careful, because there's lots of tricks. The perpetrators are very clever. okay, and they know about how to make latex fingerprints, and they know how to steal somebody else's hair follicles, and they know how to do all kinds of little tricks to confuse you. And you have to be a smart detective and a careful one. And not that I should be an example of that, but shit, that's how it turns out apparently. Little things that don't fit bother me. Okay, when it just doesn't, when you're putting that round peg in that square hole and it just doesn't look right, I apparently have that kind of intelligence where, I might not know exactly all the details, but I know that round pegs aren't supposed to go into square holes, and vice versa. Something like that. So anyway, it just, because these are flaws, it shouldn't have taken me to find them. A scientist, somebody who actually does physics, should have paused and said, this isn't a complete answer. This isn't good enough. And you don't have to look that hard. That's the whole point. I mean, Feynman sort of recognized some of the smelliness, okay, the inconsistencies that existed. And his reaction was to say, well, if I can't find the right answer, you can't do it. Some kind of thing like that. And I don't think he tried very hard, because it doesn't take much thinking about, like, photons, for example. I've pointed out something obvious, like the polarization. Well, let's go to the first thing, right? So you're just inundated with this same argument over and over, and all the physicists just accept it. They draw their photon as this thing with a lot of humps, right? Yeah, you know what I'm saying. It has more than one node, and they say photon. Now, they could draw it with 6, they could draw it with 5, they could draw it with 4. They never even talk about it. Well, how much of this is a photon? Is one of these, is just one of these a photon? I mean, if I go like that, and I go like, right, the opposite of that would be, to just do this. Is that a photon? Am I done now? I mean, a complete cycle, I guess, would end up there. So just draw an infinity symbol? So why don't they say that's a photon if they mean it's a clump, particle wave duality? Because when they say it's a particle, they're essentially saying, something like, this whole thing is a particle. And you're saying, well, how can it have a frequency then? I mean, how can a particle, a big giant thing like this, how can I say that has a frequency? I'd have to say that to have a frequency, I have to have a timed event. Something has to happen over time. So there has to be elements to it that happen over a period of time. That's not where you can have a frequency. So when they're saying wave particle, they have to compare this, something with particles, to this, something with nodes. It's the only way to make it sensible. So right there's a, you're saying, well, what, nobody could figure this out, that they should actually talk about what a photon is? I mean, they shouldn't just draw this thing and say, okay, a photon is something like some sort of expansion and contraction, but it's only one. And it happens instantaneously. A photon hits, bang, that's it. The whole thing hits at once. Well, how can the whole thing, again, hit at once? It's a frequency. It has that element to it. So it has to be produced in pieces, waves, and it has to be received in waves, right? So it can't be a wave. It has to be waves to have a frequency. They know that. And so the right answer is the fact is whenever you measure the thing, it has a length, a size, an amount. And that's the trick, right? That's and then it just kind of falls into place, because they say, well, frog can see smaller photons. It can see that photon, where we need this much photon. And it becomes kind of a, oh yeah, that makes sense. Maybe that's not the right answer, but at least it makes sense. At least it's a point relevant to what's missing from their description. They're completely ignoring something fundamental. So, my version of that would be we can see maybe 6 of these things, and maybe a frog can see 3. You only need 3 hits. But they're hits. This is the photon in the sense that this is the bit of energy, the quantized bit. So this is this is something that should have come up. What is a photon? Is a photon the unit of a frequency? The clump that's causing it, the thing the frequency is made out of it, or is it the frequency? That is, how many of these things hit? And they just totally ignore the subject, like it's not a subject. It's a really important subject. Then the other one was polarization. They just keep saying the word. I mean, me and conventional physics agree that polarization is sort of a line. You could just draw it like that. The photon's coming at you, and it's coming at you with a dimensionality. That is, it has a length in one direction and no length in the other direction. No width. It has a height, however you want to describe it. So when there's mixed light, it's coming at you in all directions. So they call that, so you call it circularly polarized, you call it lots of things. But anyway, it's polarized in every direction because some of the beams of light are coming one way, some of the waves, or whatever you want to call them. So again, it doesn't make sense for waves. It doesn't make sense that you could have a compression in a direction, that somehow it's compressing here, but it's not compressing at this angle, and it's not compressing this way, it's only compressing this way. So as a compression wave, that doesn't make any sense. Polarization. And then the real key thing is that the polarization is rather gigantic. I mean, it's thousands of atoms, 2,000 atoms of polarization, of width. So the wave is humongous compared to the size of one single electron. 1,000,000 times bigger, 1,000,000,000 times. It doesn't matter how, it's so big, it doesn't matter how insane you make the relationship. It's just an insanely disproportional size relationship. I can't even give you a human example because it's you and Mount Everest. You're going to have a relationship with Mount Everest? I mean, it doesn't make any sense at all. So, but if I make the frequency, if I make the polarization just something like the bits, the quanta, the little hunks of energy, the nodes are out of a perfect alignment. So they're all moving parallel, but they're a little bit out of alignment because electricity had to move through the wire. Because everything that's in the universe is moving while it's producing a photon. Newsflash. But the key ingredient is really the electricity. It's showing you the speed of the electricity going into the antenna. That's what this polarization is, and that's why radio waves have very large polarization. Antenna polarization is what they call it. Well, light really has antenna polarization too. It's still affecting atoms one at a time, and by affecting them I mean it's moving their electron, and it moves their electron in a direction, and when it moves it in that direction, it changes the field. Now this is something completely knowable, intuitive, sensible. This makes sense. It's not bizarre. I mean, this didn't take a huge amount of figuring out to go that, well, the photon has to be made out of units because it's a frequency, so it has to be a composite object. The evidence is that, yes, the photons that frogs see and the photons that we see, the only difference they have is, it's missing one of those. Okay, so the frog can see this one. We can't see it. Okay, that's it. It's not it's again, it converted into your wave theory. It just means that you're taking into account for how long this thing is, this irritation in your ether. Okay, and then it has a length, and the length is important. Again, for them not to even bring it up, it's not in a single video I've ever seen where they ever talk about the ray length, ever. And there's again, they're supposed to be smart people. They know what they're talking about, all this kind of crap, and they left something that obvious out of the description, out of the analysis. We're not going to pay any attention. That's like the crime investigator saying, I don't care about fingerprints. I don't care if there's DNA spread all over the place. It's a fundamental feature of understanding the energy. Again, just the fact that they imply that photons just arrive. That a photon is going through space and it hits an object and that's it. When clearly it's a frequency. It has to take time. It has to take time to make one. It has to take time to absorb one. Not even discussed. I'm just saying. And you people are so defensive, and so you're saying, oh, I'm just such an evil, snarky bastard for pointing this out. No, I'm not. So we'll play this. This is just he's doing 3 minutes on the subject, and it's just garbage. It's such trivial, silly, underexamined. It's just religion. It's just I'm just gonna gloss over all the inconsistencies and all the nonsense, and I'm just gonna tell you a little fable.
Hello, hello.
So this is the part, like I said, he's got a fan on, right? Because he's wearing a scarf. I guess he got too hot wearing a scarf, so he's wearing a scarf to be whatever, colorful. And you can hear the fan in the video. It's just like, what the fuck?
I'm sure you're all familiar with the fact that light is a duality between particles, which we call photons.
So again, particles we call photons, and the only rational way to understand particles making a photon to be even parallel to a wave is to understand the frequency is the key element, and so therefore you have to understand, or you should, that a photon is a composite object. It's made of elements, and you could call the element a force bit. But if you call it a photon, then you're confusing the emergent thing, okay, the number of interactions, with the thing that's doing the interacting. So again, it won't really work to call the individual bits photons, because one of them, a frog can't even see it. I'd argue that one of them is gravity. Okay, it's not light. Without the frequency, there is no photon. So to have a frequency, you have to have more than one thing happening. Therefore, it has to be a composite object. But he won't say anything about that.
And waves. If you want to explain interference patterns, two-slit interference, one-slit interference, or if you have gratings, all forms of diffraction.
So he said diffraction, right? So in his own lecture, he says it's interference. So in his own lecture, he makes this emphasis on the point it's not diffraction that's causing the pattern, it's interference. And here he doesn't bother. So it's sort of like Feynman. Feynman says it's not a wave, and then in another interview he's like talking about waves in the swimming pool and waves, and it's what the hell. Sorry, you can't do that and be credible.
You can perfectly explain.
Alright, so he just said it. You can perfectly explain. So this to them is perfect. So I'll just draw the diagrams again and just point out how it doesn't perfectly explain. It explains imperfectly. Pitifully. Nonsensically. So he's saying single slit. Alright, so there's a single slit. Now, we know that water will do this. Alright, I put waves in, water will do this. That's not going to make interference, okay? That'll just go up here and it'll just hit the surface and create agitation across the whole surface, especially if I curve the surface to be fair, equidistant from this wave. Is just going to be an even impulse, okay? There won't be any pattern at all. No pattern, no nothing, okay? So that won't work. So he knows and I know that it has to have, for it to work as interference, you have to have two sources. So that's what the math explicitly does. The math explicitly has this distance in the math, right? This is the important variable. That's why they put variables in math. is because they're important. So the distance that you're viewing is important, L, that's in the math. The distance between these 2 points is in the math, okay, because those are the important variables. So look, I shouldn't even have to say that to anybody, right? We already know that math is a formalization based on just the elements that have something to do with an eventual outcome. And that's all. It's just identifying the variables that are most significant, relevant. So these are the relevant point sources. Now there's 2 of them. Okay, it's a single slit, but there's 2 point sources, and they're to represent 2 waves. So their theory is, okay, the only way it works is you have to have 2 waves. That is 2 independent point sources that are going to create vectors. We're going to explain the pattern by comparing 2 vectors. This vector is made out of 3 nodes, and this vector is going to be made out of 4 nodes, and they're going to have nodes at the same place. So if I move this a little bit over here, this would be a half a node. And so those 2 would be out of phase. So it's only the places that it's in phase. And there's only a certain number of them. That's it. There's a certain number of them, and that's all there are. Okay? Just as there's a certain number of frequencies in this distance, this pattern is mirrored on this arc. Okay? It's that simple. This pattern is mirrored on this arc. How many frequencies you have here is how many nodes you have here. And it's that simple. All right, so you put the frequency of the light, and that's another one of the important variables. You need to say 500 nanometers for the sake of argument. And that's it. That's all you have. I suppose camera's not being very cooperative. Anyway, so to make it work, this has to be your point source. So this is just being fair and rational. The only place you can put the wave is here. See, the wave is creating a vectors. Okay, so the only place you can put the wave is right there on the surface. That has to be the center of the wave. So the 2 waves have to go. The water comes in here, the mechanism, the stuff, the light, and somehow it splits here in the middle, and it goes way over the edge. Now, water doesn't do that. No wave we know of can do that. No wave goes through the object, okay, the impediment. So that doesn't work. But we know that scatter, if I was just to understand it as scatter, and say the surface was scattering something, well, I know that will create exactly what I'm looking for. That'll create something that looks like a wave. It's not a wave, it's just scatter. Each photon goes a different direction a little bit. Each bit of the photon, let me be more precise, the composite objects, the photons, okay, composite objects are broken. One goes this way, one goes this way, one goes straight. And the pieces arrive here. Different pieces arrive here, and where you put them back in phase, you have a new photon. And where you don't have a photon. It's that simple. So that simple explanation solves the duality problem, solves this, how do you make 2 waves? It doesn't make any sense. Why would the waves be on the point sources? Why would the centers of the waves be on the surface? That doesn't make any sense. They should be out here somewhere. The 2 waves should be here, right? I mean, if you were going to use your Huygens gimmicks and the rest of it, that's where your 2 waves would be. That doesn't make any sense either, but I mean, it won't mathematically work. This distance won't give you the right answer. So this is the only distance that works. The clear, easy explanation is, yes, scatter works. Particles work. Particles explain the experiment. Okay, double slit. Now, they know there's 2 patterns. I've shown how they don't care. Okay, Professor Lewin did MIT videos. Didn't care to talk about it at all. So he made no mention, no conversation about the 2 patterns. Just wasn't important to him. Okay, didn't mean anything. And the 2 patterns are just identified by the fact that there's a break here, implying what was called an envelope. Okay, that you have an envelope with a single slit pattern here controlling this other little pattern here. Okay, and so you have the same circumstance, right? So if use their logic, which is hard to do, right? This two-wave thing. So the Young drawing completely fails because the distance is this, okay? And this distance won't give you the right answer for either these or this. It won't give you either one in the right place. This distance here. And the only thing that really works, mathematically works, completely works, is to do just what I did in the single slit. That is, we know these are the sources here. These surfaces. Okay, the surfaces are controlling the experiment. And the wave centers here, and here, and here, and here. And that's where the pieces are coming from. And the simple truth is that these two surfaces, the ones that are very few wavelengths, they're making this big giant pattern. And this wider surface, this distance, is making the little pattern. Okay, the smaller bars. There's more wavelengths. Right? Remember, we're just casting this image on an arc. I'll put the arc over here. You'll see it better. That's all you're doing. You're just casting this image on this arc. So the image created from here and here, okay, is creating big bars, right? And the images from here and here are creating little bars, but there's lots of frequency, so the bars are small, little ones. Okay, and the places where all four of them line up, that is, these two are in phase with these two, a full node of difference in the wave, a full node of difference, not a half a node, but a full node of difference, well, you have light. And where there's only two contributors, no light. Light, no light. Okay, and the little dots inside are just telling you, you have four contributors here. You don't have four here, so it's dark. You have four here. You don't have four here, it's dark. That's it. See, that's a complete explanation. That works. So just understanding scatter again succeeds. Waves, so now you're saying the waves are doing this. I mean, it really starts to get ludicrous, right? They break in places they shouldn't break. They exist in places they shouldn't exist and break. They go through the impediment and break in two. I mean, it makes no logical sense. Huge failure. Wave theory fails to explain the experiment. Scatter, particle theory, explains it perfectly. So they got it exactly wrong. The nail in the coffin evidence is actually the opposite conclusion. So Professor Lewin has actually said the words. It was nail in the coffin evidence. This stupid Young drawing that's just so inaccurate, right? Drawing the double slit as just two waves. Two waves can't explain the complex pattern. It has to be four waves, and they'd be in ludicrous places. But he's actually called it nail in the coffin evidence. And clearly what it is nail in the coffin evidence for wave theory. Waves are dead now. Because the only thing that was making them alive was this experiment. Everything else indicates particles. Everything else indicates clumpiness, as Feynman would say. That the universe, this energy stuff, is made out of clumpiness. So all the other experiments say clumpiness. This experiment says waviness. Right? And I've just shown you the waviness is an illusion. It's not real. If you did any kind of analysis, if you actually tried to attempt to draw it actually correctly, and you didn't keep distorting it and pretending the double slit doesn't create the complex pattern, if you pretend because you make an infinitesimally small slit, well, why would I do that? Why would I make an infinitesimally small slit? Why would I use that special case? When I'm going to do the analysis, why wouldn't I use the analysis where there's all kinds of different slit widths? My answer should be the same whether the slit width is really infinitesimally small or very large. I should have the same solution to the problem. Yeah. So, I mean, I can't do anything more than reason with you. That's all I can do. I can tell you that these things that they have said for decades, since Einstein, again, all these superficial, kind of just sloppy and made up solutions, God of the gap answers, and you can see the evidence of how they always jump to these extraordinary answers and claim it's the only answer. We have to be religious. We have to be wooicists. We can't believe in a physical, mechanical universe. And again, that's why Einstein became an outsider, is because in spite of his poor contribution to the subject of gravity, he didn't think the small universe was doing any of that bent space crap. Okay.
Assuming that they are waves. They really behave like waves.
So again, they don't if you do any kind of fair analysis. And I'll argue that his analysis was completely unfair. I mean, there's a lot to like about silly little Professor Lewin. But I'm just saying that when I found out that, frankly, every experiment he did was an experiment MIT had already done in the 50s. They already came up with these experiments in the 50s. So it was just a bunch of, I'm just reading out of the Bible. He really hadn't engineered these experiments. He hadn't seen how they were gimmicked, like the radar experiment and putting the audio tone on it. So you make a superficial description of how you detect the energy. So instead of actually having to detect whether microwaves are hitting a location, instead you use the cheat of pretending that the microwaves have to be in phase in terms of the radio signal, and you can't receive them when they're out of phase. So he took advantage of the fact that radio receivers can't receive two signals. He didn't show you that there's no energy there. There's no photon hitting the surface, because there is. The simple truth is the energy still goes to all the locations. And you haven't changed that at all. All you've basically said is my receiver can receive it at this location because the two signals are in phase, and it can't receive it where they're out of phase.
Now, if you want to explain photoelectric effect, you can only do that if you assume that light are photons.
Okay, so this word photon, so he's implying that that's the word to use for a particle. Well, again, his superficial analysis. So, if they really thought about all this stuff, he'd realize that, oh, wait a minute, the photoelectric effect is just based on the fact that the way you're detecting photons is to see an electron go from here to here. You're watching an electron move, and the electron is essentially a clump detector. So you can only detect photons because you can only detect when, like, say, a hammer hits the plunger and the thing goes up and hits a bell. You can only see the photon when the bell goes off. All the other energy doesn't make the bell go off. It doesn't mean the other energy doesn't exist. It just means it doesn't make the bell go off. So you're detecting photons based on something that requires, a certain amount of energy, or there's no photon. A certain amount of interaction, you could argue. A certain amount of hits, bullets. And they have to be in the right arrangement. That is, they have to hit, with their polarization in sequence. Because what they're really doing is pushing in a wire, right? They're hitting the wire here, the first element of the photon, right? Say the photon's coming this way, and it's bits, right? It hits the surface here. And then another bit hits the surface here, and another bit hits the surface here, and another bit hits the surface here. And it's that creates the bell ringing. You have to hit it the right way to force the electron out of the crystal to cause the electrical current. So you could just argue that you're hitting a sequence of atoms, and the atoms are basically a crystal, a group. And the group actually shoves one of their bits out, and it goes into a place between the crystals. And then that place in between the crystals is a channel for the electricity, you could argue. It gets into bubble theories and different kinds of ways of understanding what happens to atoms when they're in groups. But I'm just understanding, we already know that crystals are what create the photoelectric effect. That's why metals are crystals, metals create the photoelectric effect. So it is specific to materials. But so they already, there's already plenty of evidence that if you're going to call it a photon, you have to recognize that the particle part isn't just one thing. It's a sequence of things. A photon is a composite object. Okay? Composite object. It's made of a group of bits of energy at a frequency, right? I mean, I really shouldn't have to draw this, right? I mean, I really have to. This is, you know, what? Third graders could be up to speed on this one. That you can't have a frequency without having something that happens over time. Okay, that's what a frequency is. It's time dependent. It has a period of time between the bits of it. So that's the only rational way to understand it as a particle. This is not a photon particle. You know, the photon is a collection of hits, clumps. And so Feynman wasn't even very clear on this one. So I think Feynman was clumping photons like this. He was saying this is a clump. And he really wasn't worrying about how you make a frequency out of that clump. How this clump hits something and instill some idea that it has a frequency. Well, it can only do it if it's individual bullets, and it can only have polarization, frankly, if you understand it as individual bullets that are not in perfect alignment. You know, they're all moving parallel, but they're all moving from a different location. That explains polarization. This explains the photoelectric effect. This is the correct answer. This is what a photon is. It's clumps of momentum at a frequency. That's a photon.
Now comes the issue of this problem.
Water.
When light changes from one medium to another, for instance, it goes from water to air, then it changes the index of refraction, which is in water about 1.33.
Right, so he called this a problem, and what he clearly is saying is when it's changing from densities of mediums. So if he would have, made it clear that he knows the answer, right? He knows it's the density of the medium that's causing the delay, the retardation in the progress of the photon. So something's happening as the photon is progressing through something to retard its progress. Okay, it's not getting through the substance as fast as it should. And my simple argument is because, because what photons are actually doing is pushing electrons. And while they're pushing an electron, they're not going as fast. And the more atoms I have that the photon's going to interact with, the more it's going to get retarded in its progress. So we just understand that the photon comes in, it hits an electron. While the electron is moving, the photon loses some of its C, so it goes less than C while it's moving the electron. And then it can hit it, then it leaves this electron because another piece of force hits in the opposite direction, but I don't really know if I want to get into that. And it causes reflections. But anyway, just get the idea that it moves it, then something allows it to free, so it goes back to being free. So it's going less than C while it's moving it. Then it goes back to being C again inside the substance. But it hits another electron because it's a dense material. So the denser the material, the more electrons it hits before it actually gets out. And what you're really seeing is how much the speed of light has been retarded, okay, by the fact that it takes time to push electrons. It slows the light down. So it's as simple as me just showing you. You're a guy running 10 miles an hour. I force you to carry a weight, okay, and you can only run 5 miles an hour while you're carrying the weight. And so it's exactly the same kind of scenario, and you're not going to win the race, right? I mean, against somebody who doesn't have to carry the weight, you're going to lose the race because you're moving slower, okay? And it's just a fact, and that accounts for why it takes time for light to travel through mediums. It's not at all a complex thing. The thing that's happening is that we know the interactions between photons and electrons. We know that's the key interaction in all of physics. So there's nothing surprising here at all. I mean, nothing surprising at all. And you could even understand that sometimes when this is happening, the electrons are moving, sometimes the electron moves in some sideways direction, right? And the photon is released in that sideways direction. And so sometimes the photon doesn't even travel in a straight line. Okay, so not only is it getting slowed down, it's going less than c while it's pushing. Some of the pushing is in the wrong direction. It's not pushing the electron straight because the electron's in tension, right? So the electron's already, between rubber bands, and so you come in to hit the electron, and sometimes the electron goes that way because it's tied to other electrons and they're in the way, and pushes it this way instead of pushing it straight. So some of your momentum you're losing because you're not even making it a straight line. So you're moving electrons slows down the light, okay? Plus moving them crooked slows down the light. I mean, obviously creating them more path length. So those are the ingredients that are causing the change. And the medium is completely just dependent on how many atoms there are. The more atoms in the medium that you're traveling through are, you could argue, the more efficient the crystal is. So you can put a little bit of lead in the glass, do some different things, and you can slow it down even more. So it's not a perfect correlation between the number of atoms, because the kind of atoms will dictate how much of this there is, how much wobbling you do. So with certain kind of atoms, you'll get a very straight line. You're still pushing electrons, you're still being slowed down, but it's a much straighter line. All right, now the other key to the reason why this refractive index matters, this slowing down, has to do with the fact that it creates a phase shift. So when you bang into the surface, we have two effects. We have this idea that it's going to take a little extra time for the light to get through. The angle is going to be changed. But you can sort of understand that as soon as it doesn't have to push electrons anymore, it's not going to be having that problem of getting slowed down, slowed down, slowed down. Remember, the slowing down is only little parts of the journey. It's got to carry the weight. It doesn't carry the weight the whole time. It just carries it part of the time. And so it's partially slowed down, but obviously it doesn't have to speed back up. It just gets unburdened by it's not pushing an electron. So the little bits of here, it's going the speed of light, little parts of this voyage, but parts of it's going less because it's carrying the weight, pushing the electron. So anyway, so that's the effect we have. But what the key thing is that you have a phase shift here at the point of reflection. And so you could sort of understand that with my simple argument about a pendulum. And let's say when you're pushing the electron this way, right? So you hit the electron, you move it to this position, right? What's happening while you're doing that? Well, what's happening is now this electron is moving that way. And so that's like me moving away from you, right? What does this side of the universe see? Well, it sees me disappear. You get less photons because I'm moving away. So this part of the universe is now seeing no photon, okay? No reflection off this electron because the electron's moving away. Less reflection, let's just say less. And what's this side seeing? What's the eyeball over here seeing? Can you see that eyeball? Yeah, barely. It's seeing more because there's more reflections off this little electron because it's moving towards him. So he sees the brightness. So he sees an on, okay? And this side sees an off. So while you're putting on in, you're getting off out. That's the phase shift. That's the difference between the wave looking like this and what it's really giving back is a wave that's exactly, here, right? That's the out of phase wave, the exact opposite. So, you're creating the opposite photon when you're pushing in your affirmative photon in this opposite direction, the direction it came from. The direction it came from, you're getting an off back. The direction you're going, you're getting an on. So that's the reason why there's a phase shift. I mean, it explains it. Uh, so, yeah, so you don't need more than that.
0.5, 1.3.5, but outside in the air it's 1. And so, as it emerges.
So look, the simple argument is it's 1 in space. So air is a really small influence. The light doesn't hit very many electrons. Now you could state that this is how, so much they talk about how precise and how many decimal places their math works to and all this stuff. You can sort of know that, well, air really can't be the same as empty space. So obviously this event happens over, millions and billions of interactions. And so we're not measuring it very precisely. If we give the same index of refraction to empty space and air, that is sort of a fail right there of precision. But clearly the density between air and glass, that is the number of atoms you will hit going through 1 inch of either one of the substances, is a million times different. There's a million times more atoms in the glass than there are in the atmosphere. So clearly there's a huge difference in the density, and you would expect a substantial difference in the likelihood of hitting electrons and the likelihood of having the light retarded in its progress.
In air, its speed increases by about 35%.
So again, it's just so this is intelligent physics. This is the best they can do, is actually to say something like its speed increases, when you know that no, nothing happens. The energy doesn't change any more than the fact that obviously its speed doesn't change unless it's pushing an electron. And by the way, that's the source of gravity. Moving electrons and protons is what creates gravity, because you're absorbing an element, a piece of the force, because you're changing its momentum by changing its velocity, its time. How much time it takes to get from point A to point B changes. If you have to carry the weight, you're slowed down. It's just a fact. You don't get to your destination at the same time you would if you didn't have to carry the weight.
And the reverse is also true. When it goes from air into water, its speed decreases by about 35%.
So it's kind of a silly thing to say, right? Because we know the index is 0, 1, for air. So obviously it's not anything to do with decreases or increases. It just has to do with the fact that you've put stuff in the way.
So now comes the question. When its speed changes, does its energy change?
Well, it does, in fact, and that's gravity. That's why gravity exists, is because every time an electron and proton move, they are absorbing a little bit of a photon's momentum, its capacity to progress in space. And when you change how long it takes for it to arrive at point B, you've essentially changed its momentum. So you've changed its speed. I mean, it is a fact. And you used it up a little bit. You've delayed it. Any delay is the same thing as a reduction in momentum. So yes, energy is not entirely conserved in the sense that while you're pushing matter, you don't have as much energy. But the fact is the matter moving has the rest of the energy. So it is conserved in the sense that the electron being in motion changes its energy. So the energy it's taking out of the field, out of the little pushers, it possesses that if it encounters force. It's now going to encounter force sooner, and it's going to have interactions sooner. So it's speeding up interactions. So it's going to be giving the energy back. It's just giving it back in the opposite direction.
And if the answer is yes, if your answer is yes, then please tell me where the energy comes from when it goes from water into air.
Right. So you're assuming again that the energy has to come from somewhere, and it doesn't have to. It already has the energy while it's pushing the water. So while it's pushing water, it's got plenty of energy. It's pushing water. So it's obviously got plenty of energy. It's pushing the water molecules. It's pushing the electrons. And when you don't force it to push them anymore, it goes faster. So when it goes into air, the idea is it doesn't have to push electrons anymore. So now it's back to its normal running speed. And all you did was absorb some of its running speed when you forced it to push electrons. So it doesn't have to gain any energy. It doesn't need a source of energy. It just needs to let go of the weight. It drops the weight, and now it's going back to its regular speed. It's a car. It has a trailer hooked up on it. You don't have the trailer hooked up. The trailer hook breaks. I don't have to explain where the car got more energy to go faster. I don't have to explain where it came from. It came from the fact it's not dragging a freaking trailer anymore.
When its speed goes up by about 35%. So 2 questions. The first one is, does the energy change? And if so,
the energy is changed in the universe. So yes, anytime you're moving an electron, you're taking some energy out of the universe. Yeah, because stuff doesn't get to point B. It just doesn't get there as fast as it should get there, and so there's less energy in the universe. You've slowed a bullet down. Slowing a bullet down takes energy out of the bullet while you've slowed it down. Hooking trailers on things slows down cars. And the cars, like if it was a demolition derby, you could understand that the amount of interactions in the field is going to change if I slow the cars down. If I make the cars go 20 miles an hour instead of 40 miles an hour, I'll have fewer interactions in the universe. Simple truth. Fewer collisions, fewer events will happen because I've slowed the cars down by putting the stupid trailers on them. So yes, that's the answer. And the energy doesn't come from somewhere. It just is restored back to where it was before you hooked a trailer to the photon. Photons without trailers move the speed of light. Photons with trailers move something less than the speed of light. There, we're done.
if it increases the energy, where does the energy come from? All right, have a nice day, take care, and I can't wait for your answers, because we're now borderlining quantum mechanics.
No, we've shown and revealed that your physics is underdeveloped, that it's reckless and sloppy and imprecise and undetailed, and that if you paid a little attention to the details, like how long a photon is and how wide the polarization is, if you paid any attention to those details, you'd realize that a big giant photon is not going to interact with a single electron, that it has to interact with a series of atoms to create electricity. So to be seen, the photon has to hit more than one atom. One atom cannot create a photon. It can only create an element of a photon, a piece of it. These are things you would know if you paid some attention to the details. But you didn't. You just accepted the Jeebus answer, and you're just explaining to me how we know he walks on water and we nail in the coffin evidence and blah blah blah, and it's really not. So anyway, enough of the video, I guess.
Very non-intuitive.
So again, I hate that. I just can't stand that. It's not commonsensical. Come on. It really should be. All the magic tricks can be explained, and when they're explained, you say, oh, it's so obvious. Duh. It's very sensible. He's saying the answers aren't sensible. That the magician actually makes pigeons somewhere. doesn't hide them somewhere. No, he makes them somewhere and makes them. He waves his hand and he makes a pigeon. No, he doesn't.
Very intriguing.
No, it's very disappointing. And the fact is I will be maligned and ridiculed for questioning your authority. And your authority is made out of, fluff and colorful scarves and mishy-mushy. Okay, old little fables that you've been taught how to engineer your conversation in the same exact way, to pretend the real pattern isn't the complex pattern, and to pretend two waves are a solution, and to pretend all of this nonsense. And it's a very poor showing for intellectual types. People who are supposed to be smart should know they're supposed to be careful. And you haven't been very careful at all. And you've completely exaggerated the weight of the evidence. You're pretending you have proven it, and you haven't come close to meeting that burden. And again, you will convict anybody who disagrees and call them names and say they have bad motivations and bad intentions and they're nasty, awful, horrible people because they disagree with your authority. Again, because somebody demonstrated to him that there aren't two voltages in the same location. Two different voltages do not exist in the same location on a wire. And he demonstrated a pretty good proof of why he's shouldn't be selling that story. He just called him a flat earther. Sorry, you're a flat earther. Yeah. This is their arrogance, and somehow I'm the rude person. No, they're very rude in defending their religion. Alright. So, that be all, folks. Till the next time and such. So forth and whatnot. See, I can just go over to the little bubble now, and I can just click it, and I can just say save recording. Yeah, much better.